I might use it as a learning tool too. I'll cut like pieces out of it or whatever. All right, so let's do the whole screen. All right. Can you see my screen okay?
Yeah.
Okay, let me close the 100 things that I have open first. So we have something it's called MOBA Xterm. So what MOBA Xterm, let me close Chat GPT real quick. Um, so MOBA Xterm is a terminal with a graphics forwarding um, service that will allow us to do a secure shell connection. And this X11 is going to provide a graphical user interface, even though everything we're doing is through a command line or through a secure shell. And MOBA Xterm is going to act as the client. So we're going to communicate with the supercomputer using what's called SSH, using this client called MOBA Xterm. There's some other tools that it has, like the networking, whatever. We're not computer scientists, so we're physicists right now. So we're going to be doing condensed matter research, and a lot of times we don't really care about the network tools. So all we're really using this is like a command line. So I'm sure you're familiar with this.
Yeah.
It's just the Windows command line. It's very similar, except for it's going to be in Linux. So what we want to do is once we install it, we want to go to, I already have them created here, but let's create a new session. So you're going to click this up here, start a new remote session. And once we go here, if we want to log in to UNC Chapel Hill's computer, there's two different ones. There's Longleaf and Dogwood. I'll go ahead and pull that up. So Longleaf, we'll start with it. So the Longleaf cluster is a cluster that we typically use when we need more than one computer, when we need a large number of threads and we have a program that's optimized for parallel computing, where we need a lot of processors to perform a job. Oh, no, that's Dogwood. Sorry, Longleaf. Let me back up. So what I just described was Dogwood. So Longleaf here is where they have GPUs and large memory, like RAM, and they have some hyper threading, but typically, I don't know. We don't really use hyper threading. But anyway, so there may be a point where we need Longleaf, but what I described earlier with the multi nodes, the multi computer, whatever stacks, we're going to be using Dogwood. So to log into Dogwood, what we're going to do is we're going to have to identify the host. The host is Dogwood at unc.edu. And then our username is going to be our onion. And you'll click here to specify. So you'll type in whatever your onion is here. In my case, it's Jarkeith. And that's the only settings we need to adjust. Click OK. And there's one major step that we skipped. So let's back up a little bit. So whenever we're connecting to this cluster, we need to have a secure connection. So we're going to need something such as a VNC, a virtual networking computing. And this is going to allow for us to graphically communicate with the shell through like X11 forwarding. All right, so I'm not sure if you've done it, but have you downloaded Cisco? It looks like
Yeah, I've
this
got
when
that.
you open it up. You have?
Yeah,
Have you set it up and connected and all that?
yeah.
All right, so we'll connect to that. Um, just generate. So they do make a app Duo. Did you already install Duo on your phone or anything?
Yeah.
Okay. So typically what I do is I open the app and just get the 6-digit number that they put on there. Um, but there's several different ways you can do it, I'm sure. Do you have any questions so far?
Do you want me to like follow along with you or just watch?
It's up to you. Like I said, I'll give you access to this video. So it's up to you, man. If you just want to watch, that's fine. You'll have access to the video and you can always ask me questions.
Okay.
Um, so and I'm good about responding to emails, so it's not a difficult thing. So once you do that, I'll have to restart. So you'll have over here on to your left, you'll have Dogwood. Um, yeah, it's not at UNC. Sorry, it's just dot. So let's look at this one. Um, Edit session. My mistake. So here, don't put at. It's dogwood.unc.edu. I'll go ahead and send that to you in an email. Okay, so that's the remote host. All right. Yeah, I'll put that in the email for the recording so that way you don't watch the video and then figure out you're doing something wrong. Because I'm not going to have time to edit it. I'm just going to send it to you right after the meeting. All right. So once you have everything set up, then let me make sure. Okay, so VNC, the Cisco is loaded. So you're just going to click on here, double click, and give it a moment. Yours will probably be faster than mine just because I've changed a lot of settings, but sometimes it'll take a second. Um, Once it's loaded, it's not slow. It's super fast. So, but what we're logging here, let me take a drink real quick. So what we just logged into is called a login node. And interrupt me at any point, please. This is called a login node. On a login node, let me get some photos up in a moment. I believe I sent this to you. So let's see. So this is a different supercomputer, but it explains it just the same. Have you had a chance to look over these yet?
Not yet.
Okay,
I'll look
that's
for that
cool.
later today.
Yeah. So it basically just goes over what a supercomputer is. You know, you've got a laptop or a desktop, you know, at minimum. So you basically have a normal computer. This is what I mean by a node. And then you have a bunch of these nodes into what you call a rack. And then you have hundreds, thousands. In Dogwood, there's 6,000 computers all in one room. And then there's Dogwood, and I forget how many they have, but so you've got all of these. They're called workers. And then there's these login nodes. What we have access to at the moment is the login node, and you can see here where I highlighted it. Here's my onion. Here is the computer that I'm logged in. It's a Dogwood login node. So that's where we're logged in now. So our computer's connected to the login node, and the login node is what sends jobs to these workers. All right. So, and you've seen photos. These things are big. I think that's it for here. All right. So yeah, let's just go back here. So that's a good enough explanation. So what can we do here? What is here? Okay, so there's a couple of Linux commands. I'll also share them with you. Are you familiar with ls, or are you familiar with any Linux commands?
Honestly, not really.
Oh, that's fine. So I'll send you the basics ones. You don't have to write this down yet, but you will want to, if you want to write it down. You will need to write these down to be able to remember them. They're going to be ones that you're going to be using. ls is just to list the current directory. So if you want to print out the current working directory, it's pwd, and that'll print out the directory that you're at. So where is this directory? This is Jerkeith. Okay. Well, over here to the left, one thing that's good about MobaXterm is you don't have to be as reliant with things like ls or change directory, or print your working directory. So you've got folders here. This is the same thing. So if I want to get to this file, here, let me just find something. Can you see the text, or is the text really small?
I can see it.
Okay. So let's say I want, so I have this file that has hi there written in it. I'm going to save it, Control S. And also, if this comes up, the file has been modified, do you want to replace it? I like to say autosave, don't ask me again. And then here's a progress bar down at the bottom showing when that file has been updated, because what I did when I opened it is I downloaded it to my computer, and then I edited it using Notepad or Notepad++, and then I saved it on my computer, and then it uploaded the new edition up to the supercomputer. From here on out, I'm just going to call it Dogwood or login node. So now, if there's two ways that I can access this file, I can either click on it over here. This is called SFTP. You don't have to write that down, but it's right here, this tab. If you ever lose it, it's the SFTP. Just like we had a tab here that was open whenever we started the session. Earlier, I was talking about tools. We don't use those. Macros, if you want to do macros, that's fine. But really the only thing we use is sessions and SFTP if you want to do it this way. So how do you open this in the command line though? Let's say we don't use the SFTP. So what we'll do, and if I want to access that file, I'll say, okay, let me see where I'm at. So I'll say list, let me clear everything first so it doesn't look, and clear will remove everything from the terminal. So you have like a fresh slate. So what I'll type in is I'll type in ls to list all the files in the directory. it won't show hidden files, but it shows all of them that are not hidden. But okay, so the one I want is Kyle. So what I'll do to get to Kyle is I'll change the directory, and it is case sensitive. Well, another cool trick about this that makes it a little faster is I don't have to type in Kyle. I can just type in K and then push tab, and it will already like automatically find any files that have K in them. All right, so but that was easy because there's only one folder here in their alphabetical order here that starts with K, so that's why it knew that file. But let's say I wanted to go to this folder here. Well, there's one that looks just like it. So what happens whenever I type in P and then push tab? It types PNN underscore. Well, both of these files have that. So if what happens if I push tab again? It'll show us what are the two different files that start with PNN. So now I can say, okay, I want post analysis. So I'll just put in a P, and you don't have to start the first letter. You can also put like OS, whatever, just as long as it contains those letters, and then push tab. And then enter will put you in that new folder. This squiggly here, tilde, this tilde is equivalent to your home directory. So I'll show you that in a moment. But okay, so now we're in that folder. I can do ls. Now I can see the files that are in that. So how do I go back home? I can go home by just doing cd for change directory and press enter. It knows that that is home. I can also do cd. I can do cd tilde. That'll also take me to the same place. And cd and then cd for space / home. Those are, well, let me see. Yeah, let me not do that. They have it named differently. Cd or let me just redo this. So cd / nas / longleaf / home. Yeah, the home's a little bit different for this cluster. Okay. So this command is the same thing as this command, which is the same thing as this command. So there's multiple ways to do the same thing. So these three commands will all take you back to home. All right. So we want to go back to Kyle, or we want to go to Kyle. So cd, capital K, Kyle, and then look and see what's in there. Okay, how do I open it? Well, there's different ways. Typically, what I like to use is called nano. Nano is a it's just a text editor, just like Word or whatever, but it's command line based. So nothing fancy. So you have to type in nano, the name of the program, and then I want to open the file. So I'll type that, and look, there's hi there. We can also add, more text, and then save. To save, you do Windows X. You can see that here. There's like a help bar. So is it Windows X? No, it's not Windows X. It's Control X. Yeah, it's Control X. And there you go. And then you just push Y for yes. So whenever you see that up caret, where is it on the keyboard? Is it on the keyboard? I don't believe it is. Yeah, it is. So up caret. That up caret just means the control button. They're the same thing. All right. So that is how you navigate the file and folder system using the terminal, or using bash or shell or whatever you want to call it. And then there's also this alternative way. Okay. So I use both. One is not better than the other. It just depends on what I'm doing. And yeah. Okay. So any questions so far?
No, I think I'm good right now.
Okay. So how do we run one of these jobs? Well, what I'm going to be doing for you is there's going to be three parts. So you're going to run we call them jobs. Well, hold on, let me say this. Submit the jobs. Two, you're going to monitor the jobs. And monitor the jobs. And three, record the statistics and determine convergence. Okay, so submitting the jobs, that's the first thing that we're going to talk about. So submitting the jobs, they're going to be in a folder. The folder is going to be /VOSP. Well, actually, I don't think you have access to it. All right, so you do have access to this older folder. So let's do this. So let me just do a mock-up and then I'll give you an assignment on testing yourself. So the way I run a job and the way that you'll run a job is first you have to go to the folder. We're going to be running VOSP calculations. So I have a folder set up. It's called /VOSP, or hold on. So CD, it's not /, it's just, yeah. Okay. So there's a bunch of files in here. So I'll let you know what ones that I need you to run, but they're going to be in the GAP folder, for example. Well, actually, no, let's do this. Let's do the graphene for 5-dione here. Okay. So there's going to be multiple folders here, and depending on what stage we are in, first we optimize the system. So you'll be in the optimized folder, and then there's a folder input output. So we're going to go to output, and then there's different system numbers. Just to show you, it's going to be this one. Okay, and then there's a bunch of files here. So you don't have to worry about generating all of these files. All you have to worry about is this file. It's called .sh. This is a shell file. So let's look at it. So this file is one of the most important files. It is the file that contains the commands for the worker node. So it's executed on the login node that we're in now, but it tells the worker node how many nodes we want, so how many computers we want, and what partition we want. There's multiple partitions. I'll explain that in a moment. The number of tasks per node. The number of tasks per node is just the number of CPUs that each node has that's within that partition. The amount of time, this is very important, the amount of time we want to run the job. So we have to tell the computer we have to tell the worker nodes how long we want to use them for. If we say we want to use them for 8 hours, then if our code is not finished by 8 hours, it doesn't care. It'll kill the job and we'll have to start it all over again. So we want to make sure that this number is larger than the amount of time that we think the job is going to take. So that's what I mean by statistics. So we want to make sure that that number is big enough. Well, why don't I just put this number as like, you know, I want to let me. Why don't we just set this number to like, I don't know, 100 days and 8 hours? Like, why not just do that? 100 days and 8 hours. Well, for one, the computer has a limit of 7 days, but still. So let's say, why don't we do 7 days? And that's the maximum that we can use this node. They won't let us use it more than 7 days. Well, we use something called Slurm. Slurm is it's a batch system. And what a batch system is it allows multiple people to use a big supercomputer all at the same time. And the way it does this is it puts people in line. So if you're a really famous scientist and you have a really big lab, you're first in line. You pretty much get to do what you want. But if you're a small research lab, you still have priority like over students and stuff, but you have to be careful in how much time you ask. Because if you only request 8 hours to run a code, you won't be in line for very long. But if you put 7 days for a code, you may be in line for a couple of days waiting to start your code. So it goes by, it has a very interesting algorithm that it uses to maximize the utilization of the supercomputer. So that way the supercomputer isn't just waiting. So if there's someone who needs 7 days and they need like, I don't know, 7 days and they need like 40 nodes, they're going to know they're going to have to wait a little bit. And even though they've submitted their job like 4 days ago and it still hasn't started, if someone comes in and they put that they just need 4 nodes for 8 hours, it's likely their code is going to run immediately and they don't have to wait in line. So you have to be careful. That's why it's important to know how long your code is going to take. And you'll be able to figure that out pretty quick. I say pretty quick, but anyway. Does that make sense?
Could you like repeat that really quickly again, that last part?
So this is something you're gonna have to get a feel for. It's not gonna come like quickly, I guess. It's gonna take trial and error to know how long, but do you understand my point with you don't want it too long and you don't want it too short?
Uh, sort of. That's the part I wanted. I think I need a little more
Okay.
explanation on.
Yeah. So let's see if I can get it. Yeah, this is a really important point. So I want to make sure that you have got this. I'm trying to find some kind of okay. So yeah, this is still not good for my point. Okay, so whenever you're submitting the jobs, um, So picking the time for running jobs, which is the time command here in this batch file. This will be the file that you'll mostly work in. So what you put here is going to take some trial and error. So what I mean by that is if so if I put that I only want this is 1 hour, because the way it is it's hour, minute, seconds. So if I request 1 hour, the job will run ASAP. If you run this, we'll wait in line. So what Slurm does is it'll see someone who's wanting to use the computer for just an hour. It'll let them go ahead and sneak to the front of the line. But if someone wants to use it for a full day, they're gonna have to wait in line. So Slurm allows people to cut in line if they request a smaller amount of time. So if we know how long the job takes, we don't want to overestimate. So if overestimate, wait a long time for job to start. If underestimate, the job will not have enough time to complete. All right. Does everything here on the slide make sense?
Yeah.
Okay. So we want to make sure we know. So that's why we're going to record statistics at the end. Okay. So we're going to submit the jobs. So what we need to do is we need to know how to navigate folders and file systems using SFTP or command line or shell. Okay. So you need to know that. And then you also need to know about the batch file. Typically, they end in .sh. They don't have to, but I do that. So for simplicity and for us to be able to communicate, I would just call them .sh at the end. I typically just name them like batch 0 sh or batch 1 or batch 2, and just like that. Okay, so you'll need to do that. So edit batch files, and then execute batch files. Okay. So as far as editing batch files goes, really the only thing that you will have to play with is time. Everything else I'll have set or already have set for you, like the number of nodes you need, the partition, task per node, all of this stuff down here, module purge, module load. You won't have to worry about all that. Maybe the job name, but you can call job name anything. You can say, you can call the name of the job. You call it AJ is cool. It doesn't matter. You can call it whatever you want. Um, and yes, that's what it is. So now, how do you run it? So that's the second thing that we're talking about. So we've shown how to navigate. Now I've shown how to edit the batch files using Nano. and then execute batch files. So how do you execute batch files? So all you do is you just do s batch, which is the Slurm batch system, and then you type the name of the file that we edited, which is batch 0.sh. Okay. Well, I don't want to run it right now because I've already done that job. So let me edit something real quick that will make the job likely not run. Okay. Or at least quickly. So what you do from here is you just type in, like I said, sbatch for Slurm batch system, and then the name of the batch file, and press enter. Okay. So another thing that you're going to have to record is the submitted batch job number. So and also copy and paste is a little weird. You'll have to get used to that. You have to like push weird buttons and stuff. Yeah, because you're pasting back and forth. Okay. So, and then write down job number. It'll be something like from command line or shell. So that'll be your job number. This is really important because this is where you get your statistics at the end. So you'll do this from SQU, SF, and then, yeah, you'll type that in. So what we'll do here is for me to get the statistics at the end. I know I'm jumping ahead, but it's fine. You just type in it looks like paste is not working. Let me just type it in. So it's 526 5284. Okay. All right. And that gives me the statistics. Okay. So the statistics that I want to know is wow, it looks like it is running. That's funny. Let me go ahead and it doesn't really matter. That's crazy that it's running. I was able to get 12 nodes. Anyway, so all of this is not important. Here, let me just copy paste. Yeah, we'll come back. We'll come back to that. I'll just save it there so that way we don't have to run it again. Okay. So then you write down the job number. Great. All right. So number 1, complete. Got that down. So now let's do number 2. So we're going to monitor the jobs. So how do we monitor the jobs? What I mean by monitor the jobs is, are they done yet? So what we'll do is we'll type in SQUEUE and then dash user. U is for user, and then your onion. In your case, it's, your onion. For me, it's Jarkeith, and it will give me some information. Job ID, the partition, which is Skylake, the name. It does cut off the name like early. It doesn't allow very many characters. So if you want to differentiate the name of the jobs for your own bookkeeping, I would put what's important or what's different about them in the front. And then the username and ST, that's the status. ST is status. Right now it's R for running. This is the amount of time that it's been running, 2 minutes and 52 seconds. Number of nodes, and the node list. The node list is not important. Really, the only important information that is here is it just allows us to take a quick peek to see if the job is still running. Or it just allows us to see what jobs are running. So sometimes you'll come here and it'll say like not available. It'll say let's see, stuff partition sky lake. Oh, it's not Ceph, it's SQ. So it'll say PD for pending, and it'll say other things too. But, okay, so that is how you check a job. You'll just put this command. I'll write it down. So Ceph, is it? No, it's SQUEUE. Also all lowercase for pretty much everything. So SQ. And then user, and then your onion. So like in my case, it's jerky. So, but it'll be okay. All right. So once we've done this, we've submitted the job, and then we wait 8 hours, 1 day. So pretty much you'll just come in and you'll do this, like what I typically do. So what I'll typically do is I'll run this, I'll do all of these on like Monday. And then before I go home, like in the morning, and before I go home, I'll run SQ and look and see if any of the jobs have completed. And if they have completed, then I'll move to step 3. And then if they're converged, then I'll move to step 4. But if they're not done, then I'll just wait till tomorrow. So this is what I mean by like babysitting. That's what we call it. There's weird names. So yeah, what you're going to be doing is called babysitting. So after that, what you'll end up doing is using something called Jupyter Notebook. Have you used Jupyter Notebook?
Yeah.
Cool. And this is where you can be creative if you want. Okay, so the way you get into Jupyter Notebook for Chapel Hill is you'll go to ondemand.rc.unc.edu. And this is why I wanted you to get access to Longleaf, because hey, like we're using Dogwood for all these calculations. Why we need access to Longleaf? Well, we need access to Longleaf because that's where they have Jupyter Notebook set up. It's crazy, but it's whatever. So we'll come in here, we'll start a Jupyter Notebook. And as far as selecting what you need, you just select the number of hours you want, the number of CPUs. Typically, you just want one CPU, but I do some multi-core testing or parallel processing, so I put 4, and then everything else just leave blank unless there's something that you want. But for what we're doing, that's fine. And let's say like all right, hold on. So here. So once you submit the job, then it'll look like this screen. It'll be like pending, and then you can push refresh. And then you'll see where the job is available. So now we can connect to Jupyter. And what's nice about this is it has the file system just like with MOBA. There's the file system through SFTP where you can like click on files and navigate folders graphically. All right, come on, I got a little too clicky. So same thing over here. So just like you're used to. So let me not close all of these, but I'll close some of them. So this is where I generate like the graphs and the input files and so on. So what you'll do is you'll go to a folder. I'll provide it to you, but this will be the code. The code will be the same. So I've written a really small code, and what it does is it looks for certain files. And these files only exist if the job is complete. So it'll scan through and tell us like what jobs exist, and it'll say 0 indices without outcar. So that's good. That means all of the jobs are completed. Um, so 0 indices are without convergence. So that's good. And there's 24 indices with convergence. I know that these are, you know what a contrapositive is in math?
No.
Okay. Think you guys talk about it in statistics. Possibly you may call it something else. So both if you can use deductive reasoning to explain either one of these. So if I have 24 indices total, 24 indices, 0 to 23, 0 being an indices, so it end at 23 because all these numbers total up to 24 numbers, 24 indices. So if I say I did 24 things and all of them converged, then how many of them would be without convergence? 0. So this is a contrapositive. They're both,
Oh, yeah, I see
yeah,
now.
yeah. So the only reason I did this is for redundancy, just to make sure my code isn't doing something silly. It's in general when you write code, you like this kind of stuff, even though you're like, oh, that doesn't look very clean. You don't want it to be clean. You want it to be readable, and you want to make sure that your code is not failing. And just because it didn't fail today doesn't mean it'll fail tomorrow because it's being used differently. But anyway, so that's why that's there. So you want all of them to be converged, or all of them, or none of them not converged. Same thing. So 24 num steps till convergence. Number, I don't know what this is. I need to check on this. Number of jobs that had a maximum 100 steps, 0. That just means I told each one of these jobs they can only make 100 steps. If they reach 100 steps and it hasn't converged, cancel the job. Well, it looks like all of them converge before the maximum number. So that's good. And then there's 0 indices of jobs that have not started. And that's it. These numbers here at the bottom, ignore them. They're from something, print num steps array. Let me just comment that. So it just goes through and checks everything, and then yeah, the numbers are gone. So in other words, what you would have to do otherwise is you would have to. So what this code is doing is it's opening up the folder. So we did the graphene 4,5 dione, and it's opening up like this folder, this folder, this folder, and then it's going and looking for if Ozcar exists. Well, yep, it exists. Now we're looking to see if outcar exists. Yes, it exists. Now it's going to see if it converges. So what it does is it opens outcar. It reads this file and it goes all the way to the last line, and then it counts up like I forget how many lines. It goes up to this line, and if this line exists, then it says it's converged. So what you would have to do otherwise is you would have to open this file and then look for this. And if that line existed in there, good. That job's done. So I just made a code to make everyone's job easier. So this code, you'll have access to it. So don't worry. Um, And if you edit it and mess it up, that doesn't matter. I have a backup, so it's fine. And so that's that step. And then log, well, not log in. You're going to start Jupyter. Okay. And then record the statistics. So you'll run Ceph and then the job ID. And you realize this number is different for every job, right?
Yeah.
Yeah. Okay. And so you're going to record the statistics. So I'll let you do that any way that you want. If you want to design a code that does all this for you, totally fine. If you want to do it manually for now, totally fine. But I'm not trying to be like mean. I don't want to wait. So if you want to start with an Excel spreadsheet first and then like develop a code, cool. But your primary objective is 1 through 4. But if you want to spend extra time and like make something, or if you're like, Jared, the way you're doing it, I think this way is better, please go ahead. So that'd be great. But what you'll do, but for now, I absolutely need to know if the jobs are completed or not. And this is how you'll do it. So, well, like I said, I'm giving you creative freedom, but for now, we'll do it this way. So you have Excel or Google Sheets. Maybe we'll do like a Google Docs or something for now. Yeah, let's do that. So let me. This is the most important part. Well, it's Google Sheets, not Docs. Yeah, UNCG got rid of our Gmail, so we're using Outlook now. So let me go to Sheets. It's not what oh my goodness. Stop Google. I clicked on the wrong one. Okay, so what we want the job ID. We want, I can, let's see, job ID. Okay, so basically I just want you to put this information into a spreadsheet. So you'll have job ID, nodes, course per node. Yeah, just like that. So for like this one, we'll do 5, 2, 6, 5, 2, 8, 4. And then nodes, it's 12, course per node, 40, blah, blah, blah. So you'll fill in all of this that's yellow. You can copy and paste, whatever. So this is what I mean by you could write a code that would read all of this and do it automatically. But for now, let's just fill in the spreadsheet. All right. So you'll do this, and then one thing that's not here is convergence, and you'll either put Y or N. So whenever you run this code that I showed you a moment ago, if it comes back and it says that, I'll change the language on here so it makes a little bit more sense, but basically if it says that your job is converged, then you'll just put yes. If it hasn't, then put no. So if you put yes, you don't ever have to look at it again, you're done. Well, if it's no, then you're going to have to rerun the code and record the statistics, and then you'll have two different if statements. If converged, else. Okay. So if the job is converged, yeah, so if the job is converged, then you're done. If it has not converged, then we'll run, we'll go back to Jupyter Notebook, and run a different code. In this code, we'll just a second. Yeah, we're almost done. Oh, I'm already in the VAS folder. Okay, I want to go back. Okay, so check convergence. So let's check convergence. Lost. Check convergence. Okay, so you'll run this run notebook. Lost check convergence. So you'll start. So if it's else, if it's not converge, I'll just put if not converged. Then you'll start Jupyter Notebook, and then you'll run notebook VOSP restart job. So then you'll run this other code that will basically do this. I'll show you how it does it, man. How I'll show you what we would have to do manually and what the code does. So what it does is it will open this folder, and it will take what's called the outcar file, which is what we were looking at earlier, and it will search for the coordinates here, and then it will, you remember the whole XYZ business that we did when we were making like Pyrene and stuff. So what it'll do is it'll grab the XYZs from here, and then it will close that file after it copies those, and then it will open this other file called PauseCar, and then it will paste them here, and then it will delete all the old output files, and then you'll just be left with the input files, and then you go to redo step 1 through 4. So yeah. So that's yeah, I don't like how that is. So yeah, so you'll do steps 1 through 4. And then after step 4, if it's converged, you're done. If it's not converged, then you follow these steps. And then after you do that last step, the run the notebook, you're gonna redo steps 1 through 4. And you're just gonna do that over and over and over and over, but with different jobs. And then after we accumulate enough data, so once this Excel notebook starts getting like, I don't know, like even just 5 or 6, it doesn't really matter. So if it's just like 5 or 6, then we're going to start doing some performance graphs. Let's see, what is it called? Benchmarking. So then after we run some codes, what we'll do is we'll compare like how well they've done with the number of cores. So typically as you increase, and this is why it's super important. So as we increase the number of cores or the number of CPUs or the number of nodes, the faster the code will run. That makes sense, right?
Yeah.
Yeah. You have more workers, the job gets done quicker. Well, what if you have too many workers? What I mean by too many workers is there's not enough stuff for them to do. Sometimes they get in the way and it makes the code slower. So you can see right here the blue line here, their benchmark 1. If we see a trend like that, we want to run the job at like 140 cores, because if we end up using too many cores, there's going to be workers that get in the way and the code's going to be slower. We don't want that. So we want to find where is the sweet point, and that's what we're going to graph here. So pretty much like your contribution to this will be getting the data for this, and then additionally your contribution will be that's what I want you to start with. But what the data that you're creating is doing, um, that doesn't describe it well. Let me think. Yeah, this is my laptop. My desktop has it, but I think I may have it. Let me try. All right, here we go. So this is basically the application of all of this. So what we're doing is we're creating a screening library of in silico. In silico just means we're using a computer. So we're making, so like whenever you study things, it could be in vitro, in vivo. So meaning like we're studying it while it's in the body, or we're studying it on the lab bench. Well, we're studying it using a computer. That's what in silico is. Pyrene based, pyrene graphene based sensors. So this project is with the U.S. Army DevCom Center, but this is public information, so it's nothing that's like secret. Um, but I mean, it's common sense. Like the military, they want to be able to detect hazardous molecules, right? Like it makes sense. But what's special about ours is whenever the molecules of interest interact with the let me see if I can actually hold on. I can draw on here, annotate. Um, yeah, so here. So what's important here is we have a color change. So whenever we put this little ammonia molecule into solution, the solution being just pyrene on graphene. Well, it's not really pyrene, it's pyrene with two oxygens. It's called dione. Um, it's a yellow color. But whenever ammonia is introduced into this yellow solution, it turns clear. So what's cool about this is we've essentially have a sensor that changes color when it detects its target. But how do we know what sensor to build? Because this isn't this only works with ammonia. So what if we want to detect something different? What if we want to, let me see, I have to close the, what if we want to detect like one of the, can you see my purple mouse pointer?
Yeah.
Okay. So what if we want to detect this one? We know how to detect ammonia. We use this pyrene dione, 4,5 pyrene dione, and we get this. Boom. Cool. Awesome. Um, but what if we want to detect, like this guy right here, or anthracene, which is the two benzene rings. So if we want to detect anthracene, so what do? We need to do some tests. Well, we can run 4,5 pyrene dione, but then we notice there's no color change. Okay, so let's try 1-methylpyrene, no color change. 1-hydroxypyrene, no color change. So we're in lab using up a lot of time just manually testing these. Well, what if instead we use these in silico or computer made sensors? So we're simulating a sensor by taking the pyrene that you worked with before, but putting little functional groups at these different sites, 1 through 10. So like here on 4,5 pyrene dione, you have 2 oxygens, which are shown in red, at sites 4 and 5. And then here, 1-methylpyrene, you've got 1 methyl group, just carbon and 3 hydrogens at site 1. And then 1-hydroxypyrene, you've got an OH group, so essentially like an alcohol. You have an OH group at site 1. Well, we have a whole bunch of functional groups. There's like 1, 2, 3, 4, 5, 6, 7, 8. So there's like 16 right here. Well, hold on. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So we have like 16 shown here. Well, there's more than 16. But if we just say, hey, we have 16 of them and we have 5 different 2D materials, so maybe like MOS2, graphene, hexagonal boron nitride, tungsten, or different 2D materials. So here's like the side view, just like you remember graphene. These others are flat like that. They're just different atoms. So that makes sense, right?
Yeah.
And plus we have vacancy defects. We didn't really talk about that too much, but vacancy defects are basically where you take out a couple of atoms and it like changes its ability to interact differently. But anyway, and plus we're going to be doing something called configurational space exploration. It's like a high throughput method. I'll talk about that later if you're interested. But essentially, you've got 2,400 different experiments that we have to run. It takes like to do this like one experiment right here for 4,5 pyrene dione and be able to see this yellow to clear color change. This can take like a week to do in the lab. So this could take like 2,000 weeks. That's too long. So this computational method is going to speed this up. Well, the conventional way is using DFT. That's what we use last summer. Remember using DFT? We used Gaussian.
Yeah.
Well, if we did 2,400 of these, it's going to take years. We can't do that either because, we were saying it already takes years using the experiment. So, like, it doesn't really help us. Well, what we can do instead, and what I mean by taking years, I mean taking this whole system and simulating it using DFT all at once. Well, there's a trick we can play with machine learning or neural nets is we take little pieces. So we take the pyrene, we take the 2D material, and we take the target, and we run those through density functional theory. But they're really small simulations. Like this one, there's only 4 atoms. Here, there's like 20. Here, this is the cool part. Here, yeah, there's like 200 atoms here. If you flip it over the other way, it's like 146 or something like that. And this is truncated. It's much bigger than that. It's much bigger. So you've got like 140 atoms here. Well, guess what? Every single one of these systems has this graphene in it, right? So you don't have to do it for every one. You just do this right here, this big one time, and it's good for all the simulations. Does that make sense?
Yeah.
Yeah, because they're the same. So really the only two that we have to generate for training data are these little ones. This one has like 26 atoms. This one has like 4. So we're able to do those DFT calculations very quickly, and we use those to train this potential neural network. And then we give these whole big systems into the neural network, and it gives us the same output that DFT was, but in days instead of years. So that's the whole point of this project. So what your uh, contribution is here is to help us generate training data. So, and we need a lot of training data. We don't know how much we need, but we need to know. So, and it's just it's a lot of stuff. But anyway, so yeah, that's pretty much what it is. So, and how are we going to know it's a good sensor by using the simulations? Is we're going to look at changes in energy. I'll be able to show you that later once we have more data. But essentially, we run the simulation. We notice there's no change in energy, so it's approximately 0. Whenever we introduce the target, so if the energy doesn't change in the system when you introduce the target, then it's not interacting. It's not changing anything. So that's not a good sensor because if it's inert, then it's not going to sense anything. So we're looking at one sensor that has a greater than 0 change in its energy when we introduce the target, which is ammonia here. Does that all make sense? Is that somewhat clear?
Yeah.
Okay. So that's the science behind it. But what I'll have you do first is I'll send you an email this weekend. Tomorrow's actually my daughter's birthday. She's turning 3. It's crazy
Oh, well,
how
happy
fast
early
things
birthday.
fly. Thank you. This is her first birthday that she's actually like excited. So it's really cool seeing her. She wanted a race car bed. She's killing me, but she's an absolute mess. But no, so we're doing that tomorrow. But this weekend I'll have some time, and I will, you know, I'll go ahead and send you this video so you'll have that to refer to. And I'll also give you this PowerPoint. I'll add a couple things to it. And I'll let you play with it over the weekend. And if you want to meet, like, I don't know, whatever day is good for you next week, and see what your progress is. And then that day that we meet next week, I'll give you like the actual jobs that I want you to do. And from there, you're on your own schedule. So whenever you can do it, you do it. You can do it at any point.
Okay.
Some of the stuff you can do from like a tablet. Like you don't even have to have like your full computer. And if you can't do a bunch of these, and if you're like, this isn't for me, that's fine too. But the cool thing is about you recording the statistics and saying if the job is converged or not in that spreadsheet, I'll know like what jobs are done, and that way I'm not doing the same job. So I'm doing the same thing you're doing. I'm just trying to get more people to help me do it because there's hundreds of these that need to be done. And if it's going to be training data, it has to be perfect. I can't have like bad training data, because if it's bad training data, then it's going to make a bad neural network. So
Yeah.
you have to be really, really careful. So we're just trying to document everything just like you would in like a typical, lab. But this is computational, so it's really no different. But a lot of people that do computational work, they're actually pretty sloppy, and I'm trying to not be sloppy because I am sloppy too. So I'm trying to get a little bit more organized. So yeah, so that's what this is. Well, do you have any questions so far? And do you think you could, I don't know, maybe spend about an hour on your own before Sunday next week, and then meet for about 45 minutes next week?
Yeah. Would you put like the whatever you want me to like test out in the email that you're saying this weekend, or
Yes, yeah,
did I
that's
miss
what
it?
I'll do.
Okay. Okay.
Yeah, it'll all be together. So that
Okay.
way, yeah. So yeah, yeah, it'll all be together, and you can ask questions. I'll be available over the weekend, but um it'll be a little bit of like a learning curve, but once you get it, it's pretty much the same thing over and over, but with different jobs. It'll be second nature. Um, but I think this will also benefit you because you'll get a feel of how to run jobs, and you'll be able to put it and I'll show you what things you could put on your LinkedIn and your resume, that the skills that you've gained from this. Like I'll give you the words to use, so that way like you have a full comprehension, and I'll make sure that you know you are like um uh, competent in these. So I'm not going to say, oh yeah, you know how to run HPC systems for parallel computing. I'm not going to like. I'm going to make sure that you are before I say put it on your resume. You know what I mean? Like I don't want you
Yeah.
to. Yeah, I'm not
Yeah.
just trying
Not
to like.
not to inflate anything.
Yeah, not to inflate anything. Yeah, so I'll be there along the way to make sure you're not. And also in the future, I don't know, like you're more engineering, right? Or are you also computational or computer science?
Right now, I'm more on the engineering side of things, but I that might change to more computational stuff. I'm not totally sure yet.
Yeah, yeah. No, that is what undergraduate's for, is to figure out those things. So you're fine, man. I changed my mind a couple of times. It go figure out what you like, what you want to do with your life. So the undergrad is a fun time. So make sure you enjoy it, as far as, and I mean this like academically speaking, not like hanging out with the ag frat or something like that.
Yeah.
Yeah, so you know what I mean. So you'll
Yeah.
have fun.
And
You
the good
never know
thing,
what.
sorry, go ahead.
Now go ahead, man.
I was gonna say the good thing about the mechanical engineering at Georgia Tech is they have a concentration in nanoscience.
Ah,
So, and I'm not sure how much like the computational side of things are in there as well, but I think there's a lot of overlap with like the physical aspect of things,
yeah,
at least, and then there's some machine learning and like other concentrations as well. So
cool.
I think there's still some application, hopefully.
Yeah, 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 yeah. No, you never know. I mean, it might open some doors for you. It may not. But I do think that this is a valuable skill if you're going to be doing any kind of programming, and you need more than a laptop. Because some things do need more than a laptop. And now there's quite a few people that do engineering stuff that requires some pretty hefty codes. So I don't know. I don't know. It may benefit you. It may not. But yeah, but we'll see. I'll definitely help you and try to build you some resume and on high performance computing, and try to get your name on a publication. And yeah, it just depends on if you enjoy it or not and how much time you have, because first and foremost your priority is your undergraduate education. And if you have to say, hey man, this is too much for me, I got a dip, maybe we can pick it up Christmas, or maybe like I can't, I just got an internship, like do your thing, man. Like you're not gonna hurt our feelings. Ignatova is not gonna get you upset. Like for instance, if you wanted to apply for us at graduate school, and like like in the future, let's say you want to come back to JSNN and you want to do your PhD here, and you're like thinking back, oh man, like I was working on this project with Jared and I totally like blowed him off because I got real busy. Ignatova's gonna hate me. She's got me blacklisted. No, that's not the case at all. Um, Ignatova and I both are, we care about your undergraduate education first. Education, your education's first. Research is like lower in the list. So don't worry about that. It's not going to hurt you. The only thing that you doing now is going to help you. So I don't want you to feel pressured or anything like that. So yeah, you're not a graduate student. You will feel the pressure if you do go to grad school. No matter where you go, you'll feel the pressure as a graduate student. But as an undergraduate, you don't need to feel that kind of pressure for research. You need to feel that kind of pressure for your academic stuff, like your learning. This is your time to learn.
Well,
But yeah,
thank you for that. I really appreciate that. But I definitely am here to. I really enjoyed last summer what we did, so I'm definitely here to learn more. And
yeah,
yeah, it's all really interesting to me.
yeah. Well, awesome. Glad to hear it. Well, that's all I have today. If you have any questions about anything, just let me know.
Yeah,
Sorry I took a little bit longer than I was hoping.
no, it's
But
all good.
yeah, let me go ahead and stop sharing and all that.